Okay, so we're going to continue here in the second video, and we're going to expand a little bit on the concepts of temperature and heat that we learned about in the last video, and we're going to apply some of that understanding to calculations that involve something called specific heat. Okay, so let me give you a scenario here. All right, so we've got some substance. Okay, it's a pure substance. It could be a pure element or a pure compound. And what we know about it is we have exactly 25 grams of this stuff, and it's at an initial temperature of 22 degrees Celsius, okay, which is just about room temperature. Now, we're going to take some sort of heat source, maybe a hot plate or a Bunsen burner, and we're going to very precisely deliver 32.25 joules of energy into this object. Okay, and the assumption that we're making is, every single microjoule of this 32.25 joules is being absorbed by the object, and there's no heat loss. Once the heat goes in, it doesn't come out, and the heat is distributed evenly, uniformly throughout the object. Okay, and when we get done heating it, we measure the temperature of the substance, which we remember is, the temperature is a reflection of the average kinetic energy of the particles in a sample of matter. And the final temperature is 32 degrees, so you can see that the temperature went up by exactly 10 degrees Celsius. Okay, now let's consider substance number 2. So this is a different compound, or a different element. We're not sure which, but we also know that it's 25 grams, same mass as the first object. It's also starting at an initial temperature of 22 degrees Celsius, and we're going to do the same thing. We're going to supply 32.25 joules of energy into this object, into the substance, and then we're going to measure the temperature at the end. Okay, so after we remove, we've finished delivering 32.25 joules into the object, we measure the temperature, and we find that it's 22.3. So it only went up by 0.3 of a degree. Wow. So, so think about that for a second. Two substances, we know they're different substances, okay, but they have exactly the same mass. They started at exactly the same initial temperature. We delivered exactly the same amount of heat to each object. The first substance went up 10 degrees, but the second one, the temperature barely budged. So the question is, how can we explain this? Why such a different response in terms of temperature? Substance number 2 seems to be a lot more resistant to changes in temperature for a given quantity of heat absorbed. Okay, well, I kind of gave it away there. I accidentally clicked ahead. So it's something to do with specific heat. And there's also a concept known as heat capacity. And I think if we step back and think about these two situations, it makes sense that the second substance appears to have a larger capacity for absorbing heat without its temperature changing too much. And if you place that heat capacity on a per gram basis, okay, then that's something called specific heat. All right, and we'll learn more about that in class. Now, can we learn, using the equation that we learned about both from the book and from class, can we calculate the specific heat value for these substances? Okay, so let's just consider the first substance. All right, let me get out of PowerPoint mode here, and let me get the pen set up. All right, so the operating equation that we learned about was something that relates heat, which is Q, to the mass of an object times its specific heat times the change in temperature. Okay, and we know from the last video that delta T is calculated in a specific way. It's always the final temperature minus the initial temperature. All right, so here's our operating equation. The problem is asking us to calculate the specific heat, right? And that's this guy. So clearly we're going to have to solve this equation for C. And to do that, I won't belabor the algebra, but once you get it solved, you should have Q over mass times delta T. Okay, and remember, whenever we're solving these kind of problems, if we have to solve for a variable, in other words, if the variable that we are being asked to calculate is not by itself in our formula, then I'd like you to solve the equation for that variable first before you plug in the numbers. All right, so now let's do that. So Q is the heat, and that's 32.25. And that's joules. Okay, now here's my question. Question number 1. Remember from the previous video, heat, Q, can either be positive or negative. So in this case, the substance, this object, is the system. You can see that it's absorbing heat. So is the sign of Q going to be positive or negative in this case? Hopefully you said it's positive because it's, it's receiving heat. And you can think of that, think of it just kind of like your bank account, right? Heat is sort of like money, and when you deposit money into the bank, that is a deposit, and that shows up as a plus contribution in your checking account ledger. All right, now mass is 25 grams, and then delta T. Okay, what's the delta T here? It's T final minus T initial, so that's 32 minus 22, and I think you can easily see that that's 10 degrees even. Okay. All right, and when you get all this solved, you're going to find that the specific heat is 0.129. And now let's be careful about the units. So we got joules on top, divided by grams on the bottom, and also degrees Celsius on the bottom. And then when you get that, you put a nice box around it. Okay, so that, my friends, is how you would solve this sort of a problem involving heat and temperature and specific heat and mass. And I will leave the, you can try solving for the specific heat of the second substance as an exercise. You should get something around 4.18, but try to set it up and see if you can get the same thing that I did. Okay, here's another problem, and this will be the last problem on this video. So read the problem carefully, and the first question is, assuming that all the heat energy is absorbed by the glass, what will be the final temperature of the glass? Okay, well, let's see here. When we look at our equation, I'll write it up here. Q equals mc delta T. This question is asking for final temperature, but I don't see T final up here anywhere in this equation. That's true, but we know that T final is lurking within delta T, right? Because that delta T equals T final minus T initial. Okay, so what we can do is we can simply take this equation and we can solve it for delta T. And at the end, since we know the initial temperature, so it tells us here's the initial temperature, right? 1 degree Celsius. Since we know the initial temperature, and once we solve for delta T, we can simply use this relationship to then calculate the final temperature. Okay, let's see, a 4-gram sample, Okay, so let's do that. So delta T equals Q over mass times specific heat. And now let's go ahead and substitute in. So it's telling us we're going to deliver 32 joules. And that's positive, right? Because the glass is absorbing that heat. 4 grams at the bottom. And the specific heat it's telling us is 0.2 joules per gram degrees Celsius. Let me extend that out a little bit. Okay, and when you work all that through, you should come up with a delta T of 40 degrees Celsius. Okay, now we're not quite there yet, right? Because the question is asking us for the final temperature. And here's where we can, so now I'm going to spill over down here a little bit. I'm going to continue by rewriting, just reminding ourselves that delta T is equal to T final minus T initial. We are solving for T final. We now know delta T, right? That's 40 degrees. And we know the initial temperature. That was given to us up here, 1 degree. So all we got to do is just solve this little equation for T final and then plug in delta T and T initial. So if we solve for delta or T final, you're going to get delta T plus T initial, and that is equal to 40 degrees plus our initial temperature, which is 1 degree, and therefore the final temperature is 41 degrees. Okay, there we go. Now, let me pause the video if you need to look at that. Otherwise, I'm going to clear the boards here a little bit. Sorry, I'm getting... There we go. Trying to get control of my pen. All right, finally, how much energy will the same glass absorb if it's heated from 41 to 71 degrees? Okay, so I think we can immediately see that the delta T here is going to be positive 30 degrees, right? Because the temperature is increasing. So the question is, how much energy? All right, so this time we're going to be solving for Q, and so we're not going to have to solve for anything. So let me go ahead and just put some values in. So we know it's the mass. Again, it's the same piece of metal, so 4.0 grams. We know that the specific heat is 0.2 joules per gram degrees Celsius, and we know our delta T is 30 degrees. So this one's really straightforward, right? This one's no problem at all. And then if we go ahead and multiply these numbers, 4 times 0.2 times 30, and you should get 24 joules, because the grams, let me get my red pen here, grams cancels with grams down here, Celsius cancels with Celsius here, and we're left with joules. And so the final answer is 24 joules. Okay, I hope that helps give you an introduction to these specific heat calculations. Okay, thank you.